Hi everyone, I'm Diptanshu Kakwani and I'll be presenting the paper titled Orion Time Estimated Causally Consistent Key Value Store. We'll look at the background first. Modern web applications require geo-replicated data centers, potentially serving millions of clients at any given point of time. You can think of all sorts of applications which require such a setting, ranging from banks, social media, e-commerce, etc. Now, maintaining consistency across these data centers, given that we have network delays and failures, becomes a challenging task. Here's the general architecture of a modern web application. You have multiple data centers, and within one data center, the data is partitioned among nodes. These partitions are then replicated across data centers. Clients interact with the data center which is closest to them. In this work, we'll focus on a specific level of consistency called causal consistency, which essentially means that the order of causally related events should be the same in all data centers. So here's an example. Let's say you have two data centers, and the y-axis is the time. A user comes in and asks, "What time is it?" And another user sees this comment and replies to it saying it's 7:30. Now these comments have to be replicated to the other data center. And let's say due to network delay, the order in which the other data center receives is reversed. Now this is a problem, right? If another user queries just data center 2, they will see the comments in the reverse order. So there are two ways to solve this problem. We can either keep track of dependency or use vector clocks. Vector clocks is much more efficient way to solve this. In this work, we'll focus on enforcing causal consistency in transactions, and in particular, read-only transactions. So what are read-only transactions? As the name suggests, these transactions involve only read operations. Here's an example. Let's say you have a social media application. It allows the users to browse newsfeed or visit a profile page, all of which involves only read operations. Studies have found out that most of the real-world workloads are often read-heavy. So in this work, we present Orion, which is a causally consistent key value store which supports get, put, and ROT operations. Orion supports fast ROT using a novel protocol, which uses only one round of communication in the best case and not more than two rounds in the worst case. So let's look at the Orion protocol. You have multiple data centers, and within one data center, you have four partitions connected with each other. Each partition maintains two vectors, each with m entries, which is the number of data centers. The two vectors are version vector (VV) and data center stable vector (DSV). Version vector contains the timestamp of the latest update received from each data center. In this case, version vector at partition 2 and data center 1 contains the three values 17, 29, 14 corresponding to each data center. DSV is the entry-wise minimum value of all the version vectors. In this case, DSV is 17, 26, and 12. Partitions within one data center periodically exchange their version vector. So in effect, DSV captures the lowest timestamp after which all the updates have been received from each data center. So this was what was maintained at server side. There are two things which are maintained at the client side, which is dependency set and DSVC. This is same as DSV received from the server, but this time taken maximum element wise at the client side. So what is DS dependency set? It's a set of pairs t, d, where t is the highest timestamp of the version read, which is originally written at data center D. In this particular example, DSC is set containing only one element, 1, 13, and DSVC is 15, 23, and 12. Similarly, partitions also keep dependency set for each version of a key. So we'll now look at an example of ROT in Orion. The client sends a snapshot vector which represents the upper bound of each data center. So let's say the client wants to query two data items, with both of which reside in two different partitions. So if we zoom into partition containing A, we'll first see the DSV value of that partition. The DSV value has to be at least as great as the snapshot vector, which is in this case valid. Now we want to return the latest version which satisfies the constraint that the timestamp is smaller than what is contained in the snapshot vector. If we look at the dependency set of the key A1, we'll see that 2, 25 does not satisfy the constraint of 2, 23. So we cannot return this version. We look for an older version and see that this version is satisfied with the SV. So we return A0 in this case. Similarly, we look at B's partition and repeat the same process, but in this case, we'll return the version B1. So how does Orion predicts the snapshot vector at the client side? Here's the formula. So the client already knows the DSV. It just needs to compute the time elapsed since the last ROT while taking into account the latency delays between the data centers. DSV-C is client's DSV. CT is client's local current time. T is client's last ROT time. CT minus T just captures the time elapsed since the last ROT on client. Now we have to take into account the delays in the server side. So we subtract heartbeat interval, DSV computation interval, as well as the latency between the servers. So now we'll look at the results of Orion. Orion is implemented on top of DKVF, which is Distributed Key Value Framework. This is an open source project. We'll compare Orion with the state-of-the-art CausalSpartanX ROT protocol on YCSB workload. We use GCP and one standard 2 VMs, each with 2 vCPUs and 7.5 gigs of RAM. We use 3 data centers, Iowa, Finland, and Taiwan. Each data center has 4 VMs and 4 partitions. So now the first question which we want to ask is, how accurate is our prediction? We use mean absolute error between the predicted snapshot vector and DSV. So the closer the snapshot vector is to DSV, the results will contain the latest version of the keys. In our experiments, we run 1 million ROT and put operations. And as you can see in the graph, around 80% of the predictions were exact same, which means snapshot vector was equal to DSV. And the prediction which were wrong, out of them, 0.009% were invalid, which was the case when SV was greater than DSV. Remember, I told that if SV is greater than DSV, the partition waits for a user-defined timeout period until it sends a retry request. For a user-defined period of time 10 milliseconds, we observed that there were no transactions which actually timed out. So there was no retry at all. So communication improvement. We did an implementation optimization in Orion. So instead of sending each key in one ROT message, we combine the key per partition at the client side. So as we can see, if we increase the number of ROT keys, the number of messages did not explode in case of Orion. However, in CausalSpartanX, we see almost double the number of messages. So coming to effect of put ROT ratio. So in CausalSpartanX, put is faster than ROT, that is with default 10 keys in ROT. It causes increase in throughput as we increase the number of put operations. However, this is not the case with Orion, as Orion takes the same amount of time to process put and ROT operation. So we see only a small increase in the throughput. So coming to the effect of number of partitions. So as we increase the number of partitions, the throughput should increase. But as we can see, in case of CausalSpartanX, even with 6 number of partitions, the throughput decreased. This could be due to the messaging overhead which CausalSpartanX has. However, in case of number of 8 partition, we see both CausalSpartanX and Orion witnessing a decrease in throughput. This is due to the number of VMs which we had in the experiments. So in conclusion, we presented a causally consistent key value store called Orion, which has a novel protocol for read-only transaction. And unlike most of the existing protocols, Orion uses only 1 round of communication in the best case, and not more than 2 rounds in the worst case. We compare it with the state-of-the-art CausalSpartanX and illustrate Orion achieves up to 1.7x higher throughput and generates 10x fewer messages on YCSB workload. Thank you.